All right, I want to continue talking about graphs of trigonometric functions and transformations of those graphs. Mainly because I didn't really want to do radians last week on Thursday. So I picked this and we're just going to have to come back to radians. Which means we're technically not ready for chapter 4, but it's kind of a small adjustment to get ready for chapter 4. Even though it seems like it'll seem like it's a whole chapter, but not to worry. Just a different way of measuring it. Here's what we need to know about graphs and transformations. Last time, we talked about our sinusoidal graphs having an amplitude and a period, and how multiplication changed the amplitude or the period. It was by multiplication that we perform a stretch. And I said, what do you think is coming on next week on Tuesday when we talk about shifting things around? And you're like, oh, I don't know, addition? And yeah, that's it. Addition is going to perform shifts. It's going to shift things left and right or up and down. In both cases, we have two operations, addition and multiplication. And they can have effects that we classify as vertical or horizontal. So there's four things. Before we do that, I do want to talk a little bit about multiplication and addition, because they have some different characteristics. So multiplication. Let's talk about addition first. We got to think about what the default state is for sine of x or cosine of x before we start messing with things. What we want to know about addition is that 0 is in the middle of addition. 0 is the middle. Zero is in the middle of addition. We call 0 the additive identity. Zero is the additive identity. This is way more complicated than we need to understand, but we want to put names on things so moving forward, we can see these things show up. Identity means nothing happens under whatever operation. So an additive identity means nothing happens under addition. Adding 0 does nothing. So that's what we mean when we say 0 is the additive identity. Adding 0, no effect. Adding 0, no effect. On one side is positive. Adding positive makes things bigger. Adding negatives makes things smaller. So 0 is in the middle. So we have positive and negative. 0 is in the middle, no effect. And we have positive and we have negative. Zero is no effect, positive is an increase, negative is a decrease. Also not relevant to our interest because we care about the identities right now. Additive inverses are called opposites, 5 and negative 5. Because when we add them together, we get 0. So they're opposites. Those are inverses. For multiplication, multiplication has a different middle. For multiplication, 1 is in the middle. 1 is the multiplicative identity. Identity elements mean nothing happens under the operation. If the operation is multiplication, nothing happens when we multiply by 1. We multiply by 1, we get no effect. So since 1 is in the middle, we've got the two sides of 1. One side makes things bigger, one side makes things smaller. If we multiply by something bigger than 1, things get bigger. If something increases by 12%, we multiply by 1.12. So in the middle is 1. If we multiply by something bigger than 1, we see an increase. We multiply by exactly 1, we see no effect. If we multiply by something less than 1, but still above 0, multiplying by a fraction between 0 and 1, then we'll make things smaller. So if we multiply by something less than 1, then things get smaller. We have a decrease. Multiplication and addition have this weird interaction where things get smaller as we multiply from 1 down to 0. Once we multiply by 0, we end up with 0. That's for any system that has addition and multiplication. Multiplication by the additive identity always gets you the additive identity. So this kind of has this natural stop at 0. Multiplying by 0 always produces 0. Then what happens is kind of interesting. We just get a mirror on the other side. If we go from 0 down to -1, we have a smaller value, but the opposite side. Multiplying by -1, we just change the sign, make an opposite, and we multiply by something less than -1. Then the value will get bigger, but it'll be the opposite sign. So 0 works like a mirror. So when I talk about multiplying, making things bigger through multiplication, I want to talk about multiplying by something bigger than 1. If I want to talk about making things smaller through multiplication, we'll multiply by less than 1, but more than 0. Because if we multiply by something negative, then we change the sign. And if we change the sign, a number from positive to negative, we have made it smaller, no matter what. All negatives are less than positives. The important thing here is that 1 is the middle of multiplication. Multiplying by bigger than 1 makes things bigger. Multiplying by less than 1 makes things smaller. Any questions? Is everybody okay? So let's talk about what this has to do with transformations. What we saw yesterday is that multiplication uses a transformation on the graph of a function. Multiplication produces a stretch or a compression. Multiplication will produce a stretch or a compression. Amplitude gets taller, amplitude gets smaller. Period gets longer, period gets shorter. stretch or compression. What we didn't talk about was what addition does. Well, we mentioned it. That doesn't really count. Addition produces a shift. Graph keeps the same shape. It just moves around. Addition produces a shift. Multiplication produces a stretch or compression. Addition produces a shift. Two operations that we can transform functions with. We also know that we can have vertical transformations and horizontal transformations. Vertical transformations happen when we apply a transformation after the function. So think of our function, our base function like sine x or cosine x. If we do an operation after the function, the effect will be vertical. So we get a vertical transformation if our operation is after the function. And we get a horizontal transformation if the operation is before the function. So we have a horizontal transformation if the operation is before the function. Two operations with two locations makes four possibilities. Addition before, addition after, multiplication before, multiplication after. And so that makes us want to draw a square. We have two operations. We can do addition or multiplication. These changes can happen before or after. So if we have addition, that's going to be a shift. If it happens before the function, that'll be a horizontal shift. So before is a horizontal shift. I forgot how I'm going to color code these, so I'm going to have to just monochrome it. If I have addition that takes place after the function, that's going to make a vertical shift. After says vertical, addition means shift. Vertical shift. If our operation is multiplication and happens before the function takes place, that's going to be a horizontal stretch or compression. negative stretch is a compression. So stretch, compression. But before multiplication will be horizontal because before, and stretch because multiplication. If multiplication takes place after the function, then we'll see vertical stretch. Any questions? Framework for how we want to think about things. It's one thing to just put up a bunch of different sines and cosines, sinusoidal graphs, and read what the different things are. What we want is a way to classify each of those things, put things into groups so it's easier to remember. We could just know our trig function values for common angles in the first quadrant just by memorizing all of them. But if we organize it, it makes it easier to remember. So that's what we're trying to do here. We're trying to build a framework in which we can organize all the changes that we see. Any questions? I guess that's just a long-winded way for me to say, I do have some points. But if this was like a courtroom drama show, opposing counsel would be like, oh, objection. Does counsel have a point here? And then the judge was like, oh, I'm going to give you some leeway, Professor Leach, but you better come to your point soon. Which is, I don't know. I'm sure that that's allowed. But they do all kind of stuff on TV that's just not allowed. Like when they're like, "All answer yes or no only." At which point, all you have to do is stand up and say, "What did you want to say?" Because you get to cross-examine. So even if the judge lets one dude go like, "Oh, yeah, just yes or no," just ask him to elaborate afterwards. You know what I mean? Anyway. That one you could have objected to because I was off on a tangent. But now I'm going to get back to my original point. So all objections will be overruled. All right. Let's take a look. I did not specify what I meant by operations before or operations after. So I'm going to write my generic trig function with all the transformations that we're going to look at. So let's look at y is equal to a times the sine of b times x minus c plus d. A sinusoidal function with all the traffic. What I want to do is write down the order of operations as they're written in this function. I also want, since we're looking at sine, to let you know that cosine is also going to have the same trappings. So let's take a look at what happens if we run x through either of these calculations. In the order of operations, what's the first thing that happens to x? So let's write down what happens to x. So we start off with x, and x turns into y because a bunch of things happen. And I want to write down in order what those things are. The first thing that happens to the x. Now, the things that we're going to track are, I had a color coding in mind. I think the red and blue will go together. So red and blue will go together and be vertical stuff. So red is addition stuff, so I'll make orange addition stuff. And green will be multiplication stuff. So blue and green are multiplication stuff. Red and orange are addition stuff. Now we're organized. Yeah, they're kind of hard to tell apart. Yeah, C is orange. I don't have a better in-between color because when I break out the purple pen on the screen will look like the blue, and it's hard to tell. So I had to pick. So let's keep track of the things that happen to X. If I plugged in X into either of these expressions, the first thing I would do is subtract C. So I'm going to list that as the first thing that happens, minus C. Then the second thing that happens, once I calculate X minus C, the next thing to do is we multiply by B. So I'm just going to make shorthand down here, multiply by B. I'm just writing down the order of operations as it applies to this in this function. The third thing that we would do is either the sine or cosine. Take the result, either hit the sine button or the cosine button, whatever the function happens to say. Fourth thing that we would do, I have multiplication by A and adding D. The order of operations says do multiplication before addition. So the next thing is multiplication by A. And finally, the last thing we do is addition . So we have two operations before sine or cosine and two operations after sine or cosine. So this is what I mean by before or after. Minus C and multiply by B, those are operations that happen before the function. So up here is before the function. And these two are after. Now, if we combine before and after with what the operation is, we can see what each of these numbers are going to do. C should produce a horizontal shift. Multiplication by B before sine or cosine will produce a horizontal stretch. Then we apply the function. The shape of the function gets established. Next up, we have multiplication by A. This is after the function, so it's vertical, and it's multiplication, so it's a stretch. So A represents a vertical stretch. And finally, addition of D will make a vertical shift. So since the shifts come from addition and the stretches come from multiplication, that tells us what our default setting should be. No shift will mean plus 0. So 0 is in the middle. Because 0 is in the middle of addition. Similarly with D, we'll set D to be 0 for no shift. But B and A are included with by multiplication, and the middle of multiplication is 1. So our default setting for those should be 1. So a horizontal stretch will include 1 for no stretch. Same with A, it's 1 for no stretch. Any questions? How's everybody okay? So much background and machinery. This would be like in a game where the DM is doing a lower dump in session 1. And you're just like, oh, we're never gonna remember all this. Remember, as a dungeon master in D&D, the lore that you write is really for you. That's to entertain yourself. The players only want that information so they know which dungeons to go to so they can get the treasure and kill more monsters. You know what I mean? So it's like, do you play Skyrim to read all the books that you find? Or do you just play Skyrim to kill a bunch of bandits? I don't know. Have you read all the books in Skyrim? There are a lot. So let's take a look at these functions with generic constants A, B, C, and D. And let's look at these on a graphing calculator. Let's look at these on my favorite graphing calculator, which is most definitely not the TI-84. All right. Yeah, that'll do. Okay, so you can see I've set up with y equals a sine, but we can also have y equals a cosine b times x minus c plus d. Also wanted to have this at the end. There we go. I think cosine is blue. Yeah, that's good. There we go. So there in blue is the cosine. Notice that cosine starts at the top, then goes to the middle, down to the bottom, back to the middle, back up to the top. So there's one cycle of sine. So when I draw a sine, it goes through the point 0, 1. So I think of that as being where cosine starts. Notice that sine starts at 0 and goes up and then down and then up again. So there are the values for sine. Also note that there are 2 places where both of these cross, and we know that that happens at 45 degrees. That's when the sine and cosine are the same. That's square root 2 over 2, 0.7071. And then it happens again down here. These are all the points in one go around of the circle that Desmos will let me click on. So I can't make it any more crowded than this. So otherwise I totally would. Clear all that. So what we're going to do is go through each of our sliders and see how multiplication produces a stretch and addition produces a shift. So this first slider up at the top is, I don't know why that got listed first, but is D. Notice that the default setting for D is equal to 0. D represents the vertical shift. It's addition that happens after the trig function. Addition means it's a shift. After the trig function means it's going to have some vertical effect. So if I start changing the values of D, the graphs maintain their shape and just shift up and down. If I pause this, we can see, and include the graph just y equals D. Why does it just keep copying colors? There's so many to choose from. If I animate again, notice that if I just look at y equals D, the vertical shift, that's showing me the middle of the graph. So that plus D is the middle of the graph. I know you can't see what I'm writing. But the important thing we want to notice is that the plus D is the middle of the graph. Any questions? Stop and put D back to its default, which is 0. Check this out. Next on my list is A. A is included with multiplication, and that A is multiplied after the trig function. So x minus c, then we multiply by b, then we take the sign, then we multiply by a. So what we should see is a vertical stretch because a is multiplication after the trig function. So we can see this vertical stretch. We also see the graph seem to shift directions. When a gets to 0, it flattens out. And then we get a mirror on the other side for the negative values of a. If we pause at a particular value of a, notice that if we look at the distance from the middle to the top, that distance is 1.8. And the distance from the middle to the bottom is also 1.8. Also on cosine, the distance from the top to the middle is 1.8, to the bottom is another 1.8. So that coefficient of the trig function will tell you what the amplitude is. A is the amplitude. Notice that if I make A the opposite, if A is negative, but just negative 1.8, that is also the amplitude. It's the distance from the middle to the bottom or from the middle to the top. When we list the amplitude, we always want to list it as a positive number because amplitude is the distance from the middle to the top or from the middle to the bottom. Notice that when A turns negative, then instead of sign starting off at the middle and going up first, sign starts off at the middle and heads down first. It does the opposite. Not surprising, we multiply by -1. Things should go in the other direction. Notice that when cosine gets multiplied by -1, cosine starts off at the bottom and goes up first, rather than starting off at the top and going down first. Any questions? And when a is equal to 0, then I missed. We're just multiplying everything by 0. Any questions? That's the opening for our light zone. Let's put these back at their defaults. D is addition, its default will be 0. A is multiplication, the default is 1. Now let's see what happens when we have multiplication by b. B happens before the trig function and it's multiplication, so it should produce a horizontal stretch. So if I start animating the values of b, we see horizontal stretching and compression. So B, although it's not equal to the period, B will be the number that will tell us what the period is equal to. B tells us the period. So if I pause on a value of B, let's say B is equal to 2. Notice that the period goes from 360 to 180. We can think of the 2 as going through the X values twice as fast. We're multiplying all the X's by 2. So if we plugged in 0, 1, 2, 3, 4, 5, in sine of 2x, we're plugging in 0, 2, 4, 6, 8, 10. So in 5 steps, we go twice as far. We're going twice as fast through a circle. When B gets up to 3, notice that the period is down to 120. When B is 2, the period got cut in half from 360 to 180. 360 is our default period. That's once around the circle. Sorry, your perspective once around the circle. When B is equal to 2, our period went to 180. We were going around twice as fast. When B is equal to 3, the period was 120 because we were going around 3 times as fast. So to get the period based on the coefficient of X, we just take 360, the default period, and divide by that coefficient. Any questions? Make them all go. How's everybody okay? This is as good as the animation's going to get. I mean, this is a trig class. I mean, it's not like, we're not going to have like 3D explosions. I couldn't get the screens to rise up from the floor. Although I've always wondered if I could gear my classes with a more modern take on storytelling. Like every once in a while, just like throw in an action sequence for no reason whatsoever. It's like in the middle of class, I'm talking about like how the effect of all these different transformations on the graph, and I've got this animation going on. But what if in the middle of this, since people are like, oh, this is getting boring, instead of moving the story forward, we just stop and like I get attacked by stormtroopers or ninjas or something like that. I think that would be just like a nice way to break up the narrative. You know what I mean? If I'm losing the audience, so all of a sudden ninjas attack. So what'll happen is I'll be up here talking about stuff, and then all of a sudden ropes will drop down from the ceiling, and I'll notice. And so since I notice I'm being attacked by ninjas, there'll be a close-up of my face, not just my eyeball, and I'll just go, and I'll have like some weird expression in my eyeballs. And then the ninjas will be in front of a flashing background. They won't be moving. They'll just be like in some charging pose, and then the background is like is flashing behind them, anime style, and they just kind of like fix position, and they move up. You know what I'm talking about? You've seen it before. They don't want to animate the actual movement. They just want to give you the impression of movement by taking a fixed pose, moving it in the screen, and have the back of the screen go blah, 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 blah. At which point, they forget to mention, or they forget to notice that I have a pen in my hand. So I'm just like, oh, and I just fling the pen. And I throw the pen so hard that it hits him in the eyeball, and it flings him back. Even though the mass of this pen is like a few grams, I impart it with so much energy that a 130-pound ninja comes flying at me, and I knock him back into the wall, right? Once again, he's not moving. He just got the pen like this, and they're using this picture. And there's like blood going. And it's just the background. And then he like slams against the wall, right? That's when the other ninjas come from the other side. And I had that pen right here. But without looking, I just grabbed these 2 pens, and I fling them that way. And then two ninjas like, ah, right? And now that we've got like this tub of stuff and like these extra masks and all this other stuff, I've got all kinds of stuff to like Jackie Chan my way through a ninja attack. Like the chair's on rollers. So at one point I have to take the chair and I'll kick it to knock over somebody. Even though, I mean, if you see the chair coming at you, if you just kind of like stop moving, the chair's just going to be all. But since it's an anime, I'll go and I'll fling the chair so hard, it'll knock that person over. Right? You know what I'm talking about? Anyway. But since the chairs are fixed in place, when the fight moves over there, I'm going to try to grab one. It's going to be fixed in place. I'm going to go, huh? All of a sudden, even though I can throw a pen hard enough, knock 130 pounds of ninja against the wall, I'm not strong enough to mysteriously detach one of these chairs to beat up one of my attackers. All of a sudden, the supports are really strong. So I'm going to go, huh? And then I have to duck. Then I duck. When I'm down there, I find this eraser. Now, I'm not going to hit someone with the eraser because it's even lighter than the pen. I'm just going to slide it along the floor because it's got a low coefficient of friction. And so the ninja's going to run up, he's going to step on it, and go, whoa, 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 whoa. He's going to go right out that door. If this was a chalkboard, that's exactly what we would do. I would just grab the two and just go, poof, and then he would like come running through the smoke and I wouldn't be there anymore. I would be behind him. He'd be like, oh, huh? And then he had a big question mark above his head. And then he'd turn around and then it'd be I would have to smirk at him. So you'd have to turn around. So I'd like, oh, right? You got to smirk at your opponent. You know what I'm talking about? This is the kind of thing that goes on and why it's so distracting to do this class, because I'm imagining myself being attacked by ninjas, or like if there's orcs or something like that. Or if I just watch John Wick, it's like an endless supply of gun bugs or something like that. You know what I mean? In which case I have to use all the guns in this cabinet. There aren't any, don't go looking for it. Yeah, they keep removing my gun. I'm just kidding. No, I'd have to use pens. This is the only weapon I'm proficient with. At least I have lots of them, right? There are professors that animate a presentation that they can interact with. They like go behind the screen. So you should go watch that to realize exactly. I mean, I know you know that this class is boring already, but just see how boring it is. Watch Professor like animated PowerPoint or something like that. It's got lightsabers and everything. It's great. Let's take a break while I reset for, let's pause all these. Go back to your base. D is addition, so its base is 0. A is multiplication, default is 1. B is multiplication, default is 1. C is addition. We haven't looked at that one yet, but you can guess. All right, let's take a break. Come back in a few minutes, in 5 minutes, and we'll talk a little bit more about graphs and transfer. 5-minute timer. Oh, and we don't need to record the break.